Welcome to class. Today, we're going to start talking about modeling with first-order ODEs. All right, so here I've got a simple example of the type of models we can build under this umbrella term here, the first-order ODEs. It says a species takes 5 years to double its population. That population is estimated to be about 10,000 3 years after the species' discovery. Assuming there were no environmental factors, let's build a model for the population P after T years. And we're going to use that model to predict their population 10 years post-discovery and their growth rate 10 years post-discovery. Now, you may recall from a previous video, we know that population, or I suppose I should say the population growth rate, is proportional to the population itself. Or in other words, we expect dp dt to have the form k times p, where k is some constant. And now that we know how to solve separable equations, we know this has a general solution that p of t is equal to c times e to the kt. C is that constant of integration, or it's the parameter that defines my family of solutions. K here is the proportionality between dp dt and p. That's dependent on the model. So that's going to tell us something about how quickly or slowly it grows. Okay, so what I want to clarify here is that this is not a model for this particular scenario. This is a general solution to this differential equation. And our model follows this format, but we need to borrow the information from our specific scenario in order to find a model for this particular scenario. So there are two pieces of information that I see up here. One of those is that it takes 5 years to double. The other being, it's 10,000 3 years out. Let's do these one at a time. Let's look at it takes 5 years for it to double its population. Now, I don't know what the population is 5 years out because I don't know the initial population yet. By the way, we can maybe swap C out to be the initial population because we have sort of the implied initial condition here that the population at time 0 is, well, the initial population, right? So when I plug 0 in here, I just get C. So C must be P naught. So there's that quick notation change out of the way. But I've got two unknown pieces, or parameters, I suppose, in my model. I've got C naught and I've got K. I don't know either of them, but I do have two pieces of unused information, so that's a really good start. Let's get back to it. How long does it take to double? 5 years. And I may not know explicitly what that population is after 5 years. I know that it should look like C naught times E to the K times 5. But whatever it is, I know that, oh, and whoops, I wrote C naught instead of P naught. Just a moment. All right, that makes a little bit more sense now. So whatever the population happens to be, I know it's double what I started with. And in this way, do you notice the P naughts cancel? And I get e to the 5k equals 2. In other words, this tells me that k is equal to 1/5 natural log of 2. Great. So we found one piece of the puzzle. We still need to figure out what P naught is, but we have our other piece of information we haven't used yet. We know that in 3 years, the data tells me that population's 10,000, but the model tells me that's P naught times e to the k, 1/5 times natural log of 2 times 3 is t. And now I have a single variable equation to solve for p. P naught, excuse me. Turns out P naught is about 65/98. So what have we done here? We used our biology sense to write down this form for the differential equation, and we know this differential equation has this general solution. Then we used context from our problem to inform what the different parameters in the model are. So when all is said and done, the model for this system is dp dt equals kp, or 1/5 natural log of 2 times p. However, we know that this has the solution, p of t, equals 6598 e to the k t. And now this might look a little bit familiar. You probably remember seeing this in an algebra class. And this question here, predict the population 10 years after its discovery, is the type of problem you might see in an algebra class because it doesn't require any calculus or differential equations for that matter. Here, if you're just told, hey, the initial population goes here and the growth rate goes here, and you're told those two things, or even if you're not, you're given this information, but you're told this is the format, notice we only used algebra from this point down. So we can finish off the algebra problem. That's just plugging in 10 to p. And that tells me the population's about 26,392. But what I've written as part C here is a type of question that algebra can't answer for us to predict the growth rate. And now we see why the differential equation is actually a more comprehensive model, because it also tells us something about the rate of change of the population. I can use the other part of this model, that dp dt is 1/5 natural log of 2 times p, where the population at 10 years we just found to be 26,392, to predict the growth rate. This tells me it's about 3658.7. Or in other words, 10 years from its discovery, the population will be growing by 3,658 and some change members each year.